Yesterday we looked at 9.2 part 1, which is basically converting points that are in rectangular to polar, polar to rectangular, and graphing in polar, just a single coordinate. Okay, remember from yesterday, this is how you write a point in polar. Okay, we don't use x and y, we use r and theta. Okay, how about Victoria, what's r? What does that stand for?
Radius.
Radius? So that's the distance your point is from the origin. And Alex, what about theta? What does that represent?
The angle.
That's the angle. That's the angle that you would have between your radius and your positive x-axis. Okay. Before we graph that, okay, I'm going to show you how you get your calculator into the mode where you can graph it. Okay. It says r equals. Okay. Anytime you're graphing something that says r equals, that's polar. Okay. If it's y equals, that's your function notation. If it's x of t and y of t, that's your parametric. And this is polar. Okay, so it's a third mode. So on your calculator, okay, go to mode, okay, and change it to polar. Somebody asked me in the last class, can you make it so you see the grid? You can display the grid in rectangular, but you can't display a polar grid on the graphing calculator. You can put an image on the background for the graphing. You can do that. But that wouldn't really be like a grid. So we're not going to be able to put the circles. All right, so just change it to polar. Okay, now before I graph it, what do you think the shape is that I'm going to get here? If you graph all points that have a radius of 2, it's basically the definition of what shape? All points that have a fixed radius from a center point. Oh, Emily?
A circle.
A circle. Okay, that's the definition of a circle. You're going to graph any point you want. Theta can be anything. Theta could be 10 degrees, 20 degrees, 30 degrees, 97 degrees, negative 100. But the radius has to be 2 every time. So you're going to get points basically like that. And that's exactly how the calculator is going to graph it. It's going to graph a bunch of points, and it's going to connect them, just like it did in parametric mode. Right? So when you graph it, let's go zoom 6. Okay, notice it looks elliptical, because we talked about the screen not looking proportional. That magic number, the ratio you need between the width and length to make it look proportional, is 1.6. So if you make your x min and max negative 16 and 16, and you make your y min and max negative 10 to 10, if you divide the width by the length now, you'll get 1.6, which will make everything look proportional. Now it'll look just like a circle. Yeah?
Mine is just a dot.
You just getting the dot? All right, so the other thing you want to make sure, I would start with zoom 6. Okay? Make sure your theta min and theta max are 0 to 360. If you only had something like 0 to 15, you get just a dot. Okay, because it's only graphing the first 15 degrees. If you go beyond 360, I can show you what happens. It's going to trace over itself. You might see it. No, you didn't really see it there. But it just traces over itself twice. Okay. Any questions on graphing that? All right, so that's when you fix the radius. And you can let theta be anything you want. You get a circle. Okay, what if we switch it? This time I'm going to fix the angle. And the radius can be anything I want. Okay, this is equivalent, kind of like if I asked you to graph the line x equals 2. You can't graph that on a graphing calculator because in the mode we're in, you can't solve for that variable. Okay, you cannot put theta equals, just like you can't do x equals. You can only do y equals when you're in that mode. So we got to kind of think this one through by hand. Okay. So theta is 2. Okay, radius can be anything you want. So just make up some points and graph them. Let the radius be 1. Let theta be 2. You can let the radius be 0 and theta be 2. Radius could be 3. Just keep theta 2 all the time. And let's throw in a negative. Okay, let's graph those points. If you're not sure where 2 radians is, you might want to just change that to degrees. Okay, so if you take 2 multiplied by 180, divide by pi, it's about 114 degrees, 115. Okay, so a little bit past 90. Okay, so we're going to go out 1, and then 2 radians counterclockwise. About right there. Okay, the next one says basically to stay at the origin, and we're spinning in place. So my point would be right there. I'm going to go out 3, and then go 115 degrees. About right there. And then I'm going to go -1 and go 115 degrees. So -1, 115. If I keep graphing points, what am I going to get here? Yeah, I'm going to get a straight line. Basically, like that. So if you want to graph a line that goes through the origin, it's pretty easy to do. Just let theta equal any number. If you change theta, you'll change the slope of it. Okay, in a little bit, we'll talk about how you could graph any line. That gets quite a bit more complicated. If you want to say graph a line in polar with a slope of 5 and a y-intercept of 3. It's not as easy to do. The formula is a little messy. Y equals mx plus b, that's the way to go if you want to graph a line. But we can do it in polar, and I'll show you how. But for now, any questions on that one? That's theta equals 2. Again, can't draw that on the calculator. All right, our next graph, we can sketch on the calculator, but we're going to sketch it by hand because you're going to have some on the test you're not going to be able to use the calculator for, even if you wanted to. You can't do it. So you got to try to learn how to analyze the graph by hand. Okay, you're making a table, and then make a sketch. Okay? And we're in a totally new system now, so we have no idea what this thing is going to look like. All right, if we had function notation, we're used to those graphs. Okay, like polynomials, we know a little about the end behavior. We know how many times they can turn. All right, we have nothing to go off of here. Okay, we don't really know what's going to happen. All we know is hopefully some basic properties about sine and sine, specifically the highest and lowest values. Okay, Augustine, what's the largest that sine ever gets?
1.
It hits 1. And if you take 1 and multiply by 3, what do you get? And then plus 3 more. 6. So your radius here can never get bigger than 6. The only way that could happen is if sine got bigger than 1, and it doesn't. Okay, so the biggest sine is 1, tripled is 3, plus 3 is 6. And now I want to figure out the smallest my radius could go. Okay, for that, we've got to think about the smallest that sine could go. Casey, what's the smallest the sine function? Hits -1, and then if you triple that, you get what? And then add 3? 0. So my radius for this particular graph that we're about to sketch is always between 0 and 6. It's going to change. It's going to have a variable radius because of the sine theta. All right, so what we're going to do is we're going to make a table, and we're going to focus on 4 different intervals. We're going to focus on sine from 0 to pi over 2, from pi over 2 to pi, pi to 3 pi over 2, and then 3 pi over 2 back to pi. And if we focus on those 4 intervals, what's happening to the radius in our equation, I think we'll be able to make a sketch. All right, so first, let's figure out what's happening to sine. All right, so between 0 and pi over 2, if you plug in any angle for theta between 0 and pi over 2. We're going to write down the values that were always between. Okay, it's basically on the y-axis. Okay, let's start with 0. Brielle, if I plug in 0 for theta, how high would I be on the y-axis? I'd be at 0. Okay, sine of 0 is 0. Okay. Now if we go to pi over 2, okay, that's the end of the interval that I'm testing. Cody, what's the sine of pi over 2? Yep. 1. Okay, so now we know what's happening to sine of theta over this interval. It's getting bigger. It's increasing from 0 to 1. Now we're going to take that knowledge and fill it into this equation. Okay? The smallest that sine theta can ever be is 0. Okay? Alex, what's 3 times 0? 0 plus 3? 3. So in my equation, the smallest my radius will ever be over this interval is 3, and then it's going to get bigger. What's the largest my radius is ever going to hit? And that's when the sine of theta becomes 1. James? 6. If the sine of theta becomes 1, and you triple it, you get 3. Plus 3 is 6. So my radius, when we sketch this, is going to be increasing from 3 to 6 over the angles 0 to pi over 2. Okay, I'm going to do the same thing 3 more times. Okay, pi over 2 to pi. Andy, what's happening to the sine function from pi over 2 to pi? So it's here it is at pi over 2. Here it is at pi. So as the x values, go from pi over 2 to pi, what's happening to the y values?
It's going down.
From what to what?
1 to 0.
Yep, it's going from 1 to 0. Now we'll use that fact to figure out what's happening to my radius. Kelsey, when sine is 1, and I fill that in, what do I get for a radius? 6. How about when sine is 0, and I fill that in? What do I get for a radius? 3. So what's happening over the interval from pi over 2 to pi? My radius is shrinking again. It's starting at 6, it's shrinking back to 3. Okay, now let's do pi to 3 pi over 2. Okay, Brianna, what's happening to my sine function as we go from pi to 3 pi over 2?
It's going down.
Yes, it's decreasing again. From what to what?
0 to -1.
Yep, this time the sine function is going from 0 to -1. Now let's figure out how that affects my radius. So Darren, when my sine function is 0, what do I get for a radius? I get 3. How about when the sine function is -1? We get 0. So the radius is decreasing to its smallest point, 0 here. Okay, now let's figure out the last interval. From 3 pi over 2 to 2 pi. The radius is increasing again. Well, sine is increasing, -1 to 0. Which means the radius is increasing from 0 back to 3. Now when we sketch this and connect the points, nothing here is going to be linear. Okay, we're not going to connect any points straight. Okay? Because when it's increasing from 0 to 3, it's not increasing linearly because the sine function is not increasing linearly. Think about sine. It's increasing, but it's curved. Okay? It's not straight like that. If it were, that would change our picture. Okay, so everything in this picture we draw is going to be curved. Right, so now let's use that table and graph our radius. When our angle is 0, the radius is 3. Okay, so sketch that. Angle is 0. Radius is 3. When our angle is pi over 2, the radius is 6. So pi over 2, 6. And now we're going to connect those 2 points, but just try to curve it a little bit. It should even be a little bit more curved than that. It's as good as I can do. All right, let's look at the next part. At pi over 2, we're at 6. Okay, we already have that marked. As we head towards pi, the radius is going to shrink back down to 3. Okay? So by the time you get all the way over to pi, your radius is going to have shrunk back down to 3. It's basically a mirror image of that, okay, on the other side. So what I'm going to do to try to make it look somewhat decent, make a mirror image. Okay, next part. As we go from pi to 3 pi over 2, my radius is going from 3 to 0. So it's going to start at 3, it's going to end at 0, and as I head towards 270, it's going to head right in towards the origin. Okay, and as I go from 270, or 3 pi over 2 to 2 pi, my radius is going to expand back out to 3. Right, so as you start heading back around, your radius gets larger again. Okay, and what shape does that kind of look like upside down? Yeah, a heart. And that's where it gets its name from. Okay, that's called a cardioid, because it looks kind of like a heart. Okay, I'll sketch it on the calculator to show you how to do it. But we're going to get the same picture we just drew. Okay, so that's called a cardioid. Let's sketch 3 plus 3 sine theta. So 3 plus 3 sine theta. You can do zoom 6. Remember, this is not going to be proportional. Okay, if you want it proportional, you should do zoom square, or set your window up so it's in a ratio of 1.6. Okay. So this one looks a little bit more rounded. You can change how it looks depending on your window. You zoom in, okay, zoom out. If you change the 3s to make it bigger or smaller version. But I actually think our sketch looks a little better because it looks more like a heart. Okay, so anything of that form, as long as you keep the a's the same. You can also use cosine. Okay, what cosine would do is it would rotate the heart 90 degrees. Because remember, sine and cosine are 90 degrees out of phase. So you could have a heart that kind of points to the right, points to the left, if you use cosine. Or you could have a heart that points up and down if you use sine. Okay, if you change the numbers, like the 3 and the 3, let's say you make one a 3 and one a 2. That's not a cardioid anymore. It's a similar looking shape, but you might see it loop back on itself. Okay, that one doesn't. Let's try it the other way. Yeah, if you zoom in, you'll see it. Okay, now the cardioid is kind of crossing over itself. Again, that's not really a cardioid unless these two numbers are the same. Okay, to get a full picture, you only have to go from 0 to 360. It's not called T-min and T-max anymore. Now it's called theta-min and theta-max because we're in polar. And it's not T-step, it's theta-step. Okay. What would happen if I set theta-max to 720? would happen? Even if we wouldn't see anything, there would be something happening. Darren? Yeah, it would draw it twice. It would just trace over itself. Okay, any questions on graphing a cardioid? Either you're having trouble with your calculator or what the definition of a cardioid is.
Well, on the chart with the 3 columns,
Yeah.
the column on the left, how did you get those numbers?
These values?
Yeah.
I basically took all the, I use the points where it crosses the x-axis or it goes from increasing to decreasing. So from 0 to pi over 2, it's increasing, and then the behavior changes at pi over 2. It starts going to decreasing.
So like if that was on the test or something, you'd give us those values.
Yeah, yeah. I give you the intervals. You'd have to figure out what's happening over that interval and then how that affects your picture. Yeah. Okay, so next thing we're going to do is look at how we can take a polar equation and change it to a rectangular equation. If you have an equation in polar, what letters does it use? Augustine? It uses r and theta. And if we're trying to change it to an equation in rectangular, we want to get rid of r and theta. And what letters do you want to have in rectangular? Yeah. We want to have x's and y's. Okay, so we have a few formulas we can use to do that. You've seen all these formulas earlier in the week. X equals r cosine theta. Y equals r sine theta. We talked about these when we did parametric equations. Writing the equation of a circle parametrically. R squared equals x squared plus y squared. We did that formula yesterday. It's like your Pythagorean theorem. And finding an angle, theta is the inverse tangent of y over x. You can use any of those formulas to help you get rid of r's and thetas and change them to x's and y's. So let's take the cardioid, okay, we just had, and I want to convert this to rectangular. It's not going to be nice, but we're going to convert it to rectangular. All right, first thing I want to get rid of is this r. Now I don't have a formula up above that directly says r equals, but one of these 4 formulas I could do something with, and it would say r equals. Which formula do you think I'm going to use? I could easily get r by itself. And it would be in terms of x and y. I wouldn't have any thetas in it. Oh, Cole?
R squared equals x squared plus y squared.
Yeah, I'm going to use this one. Now, it doesn't say r equals. It says r squared equals. So what could you do on both sides, Cole? Take the square root of both sides. So r is equal to the square root of x squared plus y squared. Fill that in for r. So that's r. Now sine theta. What is sine theta equal to? Let's see what formula we'd have to rearrange another formula a little bit, but we could get sine theta by itself. Jill?
Y over R.
Yeah, sine of theta is equal to y over r. Now I just said we can't use an r, but that's okay. We'll substitute in for r, just like we did in the last one, in a second. Okay, so sine of theta is y over r, and now change r. Again, r is the square root of x squared plus y squared. And last thing I'll do just to try and clean it up a little bit is multiply everything by the square root of x squared plus y squared. That's at least going to get rid of this fraction. Okay, so multiply it to the first term on the left side, the second term, and the third term. Okay, Darren, what do I get if I multiply the square root of x squared plus y squared times the square root of x squared plus y squared?
X squared plus Y squared.
Right, the root's going to cancel out. Now if I multiply 3 by the square root of x squared plus y squared, I just get this. And if I multiply the 3y by the square root of x squared plus y squared, the square roots would cancel out. So there's the equation of a cardioid in rectangular. Not nearly as simple as it was in polar. Not even graphable on a calculator. Because to graph it, you'd have to get y by itself. And that could be tricky. Because you've got a y that's squared, you've got a y in a linear term, but then you have a y that's squared and it's a term under a square root. Okay, so it's not going to be easy to get y by itself if you had to. So that's the best we can do. So, any question on converting that equation to rectangular? Okay, so we just use those formulas you see right up above. Okay, let's try converting. Let's go the other way. Let's convert to polar. And what I'd like to do is write the equation of a line with a slope of m and y-intercept b in polar. So to do that, we need to start with just the equation of a line in rectangular. What's the equation of a line in rectangular form? Oh, Kelsey? Yeah, y equals mx plus b. Now, if you're going to convert that to polar, what letters need to go away here? Augustine?
X and Y.
X and y. Why not m and b? Why don't those have to go away?
Because M is like the magnitude.
In y equals mx plus b? What is, yeah, m is something, but it doesn't stand for magnitude. Think about when you draw a line. Well, what's b stand for?
Oh, it's the slope, and that B is just its position on the y-axis.
Where it crosses the y-axis. Okay, these are constants. M and b aren't variables, they're numbers. Okay? X and y are variables. Okay, let's start with y. Andy, how can I rewrite y?
R sine theta.
Okay, so we can write y as r sine theta. And we can write, oh, sorry, that's this, x. James, how can I write x? R cosine theta plus b. Right, so we have r sine theta equals Mr. Cosine plus b. All right. So now, thank you. So at least if we want to get r by itself, because in polar, that's what it is. R is by itself. So let's at least get all the r's on one side. Okay, how would we move Mr. Cosine theta to the other side? James? Subtract it. So subtract mr cosine theta. Subtract mr cosine theta. Now you're left with b on the right. We have r sine theta minus mr cosine theta. Both terms here have an r in common. Since they both have an r in common, what can you do with the r? Augustine?
Get rid of it.
Well, we can't get rid of it, but we can move it somewhere using the word I'm thinking of. We can, let's say, pull it out, or we could, there's another word for it. Factor it out, yeah. Factor an r out from each term. If you factor r out from the first term, you're left with sine theta. From the second term, you're left with m cosine theta. Equals b. And now my last step is I want to get rid of what I've multiplied r by, the sine theta minus m cosine theta. So how would I move what's in parentheses to the other side? Darren? Yeah, we divide it. So we get b divided by sine theta minus m cosine theta. That's the equation of a line and polar. Okay, b, actually, let's write it like this. M is your slope. And b is your y-intercept. Now you have to be careful. You can't graph this using the case b equals 0. In y equals mx plus b you can. That would represent a line that goes through the origin. But if you put 0 in for b, 0 divided by anything is always 0. So your equation would become r equals 0. You'd be drawing a picture that has a radius of 0 all the time. That won't work. Well, let's sketch a line and see how it works. Let's let the y-intercept be, say, 5. And let's let the slope be 2. So let's try sine theta minus 2 cosine theta. Okay, so when I hit graph, I should end up with a line that goes through the point 0,5. It's my y-intercept. And it should have a slope of 2. Okay, after you type that in, do zoom 6. Looked a little funny the way it sketched it, but there's our line and polar. Y-intercept exactly where we said, and the slope is 2. Any questions on that? Okay, notice as I start tracing to the right, it goes down, keeps going down, and then eventually it comes back in at the top. It's because of the way it's drawing it. But that's fine. Okay, so again, not very elegant, but you can draw a line in polar. But if I could pick, I would do y equals mx plus b. Much easier to draw a line that way. All right. So now we're going to look at how we can take a polar equation and put it in parametric mode. Okay, so pretend that you had some curve in polar. Doesn't matter how you sketch it, just any curve. And what I've done is I marked a specific point on the curve. Okay. Well, that point, if I draw a segment from it to the origin, it has a radius. And it also has an angle. T is the angle between the positive x-axis and that radius. I didn't use theta because we're getting into parametric mode. So when you're thinking parametric, think t. That's your variable. That's your parameter that's changing. Now r, the radius isn't fixed. Okay? If I draw a different point, and I draw in that radius, that point has a different radius than the other point. So the radius is changing. The only time the radius wouldn't change is if you had a circle, and the radius would be the same for every point. Well, we don't know what the radius is going to be, but we have a formula that will calculate it, and they will give you that. Okay? The formula that calculates the radius is the equation in polar. R equals, and then whatever they give you for an equation or a function. Now, when they give it to you in polar, it's probably going to have theta as the variable. The first thing we'll do is we'll change the theta to a t, because we're going to be getting it to parametric. Right? So your equation in polar calculates your radius. But if we're going to write it in parametric, we need to split it up into x and y. So I don't just want the radius. I want the horizontal part to my radius, and then I want the vertical part to my radius. And we've done what we're about to do right here many times.
Is that R equals FT?
Yep. Okay. Which trig function would I use to get just the horizontal component of my radius? James?
R squared equals x squared plus y squared.
Sorry, trig function. Which trig function would we use? You're not going to need Pythagorean theorem because you don't know x and y. You're going to know r in terms of a formula. And we'll use that formula in a second. But for now, I just want to know how I would get x if I knew r and I knew t. Alex?
What was the question?
How would you get x here, given r and t? You guys actually already wrote this formula today. There is a formula, x equals, yeah?
R cosine.
Yeah. X equals r cosine t. The only thing we don't know is r. R is constantly changing, but that's okay. You have a formula for it. The formula will calculate r for you. So you fill that in for r. Okay, and how about y? How would you get the vertical component of the radius? Darren?
R sine t.
R sine t. Thank you. Again, you might be saying, well, what's r? We don't know it. You're right, we don't know it, but the formula they give us calculates r because it's in polar. That's the whole point of polar. R equals. Okay, so you just fill in those two things, and that basically gives us our equations to write it in parametric. So to find your x component, take the function that they give you. It will be in terms of theta. First thing I'm going to do is change theta to a t. Literally, erase theta, write t, because we're going parametric. And in parametric, the first equation is just the horizontal component of my radius. Okay? So take that radius, multiply by cosine t. Second equation, that's for my vertical component. So I'm going to take my radius, which will be given to me in a formula. Use that formula, change it to t. Take that and multiply by the sine. That gives me the vertical. All right, let's try an example. Okay, so here's the curve in polar. R equals 7 sine 2 theta. They want us to change it to parametric. In this problem, this is f of theta. You can write it r equals, or you could also write f of theta equals. That's the same thing. It's just like when you have y equals 2x plus 3. You could also write f of x. You don't have to use y. You can use f of x if you want. It's just a function in terms of x. That's the variable. This is a function in terms of theta. That's my variable. Okay, so when I write it parametrically, I'm basically going to start with f of theta, except change all your thetas to t's. And that's the first thing that goes in that first equation. Okay, so how would I write that first part? Taking my equation and changing theta to t. Oh, Victoria? Yep, and so it would be f of t equals, and what would it equal on the other side?
7 sine 2t.
Great. That's the formula for your radius. Now, when you're writing it parametrically for the x one, all we want is the x value of it, the horizontal component. So multiply that by cosine. So that takes care of the horizontal. Now we have to do the vertical. Okay, Jill, what's the first thing I'm going to put for y?
7 sine 2t.
Yep, you put 7 sine 2t again. Okay, that's your radius. But now all we want is the up and down. We want the vertical component. So we're going to multiply that by what?
Sine
By sine t. That's all you have to do to change something that's in polar to parametric. Take what they give you in polar, write it down, just change it to a t. Put a cosine next to it if you want the x. Put a sine next to it if you want the y. And that breaks it up into your components. Okay, let's graph that. Okay, I'm going to graph it on this one. All right, so I'm going to change to parametric. Type in 7 sine 2t cosine t. Okay, for the other one, I'll type in 7 sine 2t sine t. Don't try to get fancy and combine the sine 2t with the sine t. They're different arguments, so you can't write sine squared or anything like that. Okay, and then do zoom 6. I have a scatter plot turned on. I'll shut that off. But that's the basic shape minus those little dots you should get. Right. Now let's type in the same thing in polar. 7 sine 2 theta. Right, so type in 7 sine 2 theta. This is just to check and make sure that what we did comes out the same when you write it each way. And go zoom 6. We get the exact same picture. Okay, just one is polar, one is parametric. Any question on that? Okay, this particular image, okay, is called a 4-petaled rose, okay, because it has what looks like 4 petals. And the number that you put in front of the trig function basically controls the length of the petal. Right? So if you put in something like 10, so you're going out on a date, you want to get somebody really big roses, you should hold up your calculator screen, put in a 10, they'll be really impressed with you. There you go. So there's your 4-petaled rose, a little bigger. Okay, the distance here you're measuring is from the origin right to that tip. That's 10 units. All right, now say your particular friend you're with, they don't like 4-petaled roses. They want more petals. All right. What do you think we could change in that equation to have more petals? Yeah,
The 2.
the 2. Sure. How many petals do you want? You tell me. This is your flower. Don't give me an even number, and then I'll do an odd number after if you want.
10.
You want 10 petals? Jeez. 10 petals. So if I put, you say, how many did you say?
10.
You said 10. All right. So if I want 10, what I have to do is put in, yeah. Well, let's try 10 theta. I want to show you what happens if you do that. Some people may say, oh, try 10. Well, if you try 10, you get like an abstract art thing there, and that's actually 20 petals. Okay, let's try 5. Okay, you might think 5 is going to work. Well, no, with 5, I get exactly 5. So 10's a tough one to come up with. If you put in an even number, it will double it. Okay, if you put in an odd number, you get exactly that many. So if you said 8, I could have done 8. You didn't ask for 8. Could have done that with 4. Okay, if you want 12, I could do that with 6. If you want 9 petals, you could do that with 9. But 10's a tough one to come up with. All right? But everyone kind of see that pattern. Put in an even number. So let's put in 4. We'll get 8 petals. I'm not sure if you can smooth out the tips of those petals and make them rounder. Let's try, let's change the T-step to 2 and see if that does anything. Yeah, it does. So if you increase your T-step a little bit, you can get nicer looking flower. Okay. So any questions on that? You like that? You could shade the petals in different colors for someone, make them really happy. Whatever you want to do. All right, if you got really creative, you could actually draw like a flower like that, and then you could put a smaller one kind of in the center of it. Okay, different color. Like if we did something like, let's put in a ton of petals so it just looks like it's almost all filled in. Let's put in like 30 petals. Okay, and this time, actually I don't want my radius 30. Let's make the radius 2. Okay, this might look kind of nice. That's kind of what I was going for. Okay, so you can make all kinds of interesting pictures there. You like that? All right, so on the test, if I ask you a question about how many petals would this flower have, and want to know how to figure it out, odd, you get the same, you get the exact number. Even, it doubles. If you start doing decimals, like 2.5, you get kind of weird things that happen. I'll show you what happens if you do that. Starts to look kind of normal. Then you get something like that. So it's like somebody's pulled some of the petals off. But again, all kinds of different pictures. Play around with it, see what you get. Okay. Something else we can draw, a little bit more simplistic, is just a spiral. Okay, a spiral is basically a shape where your radius is constantly increasing. Okay, I'm going to switch over to radians because it keeps the numbers smaller. And if you graph that, you're graphing a spiral where your radius and your angle are equal. So the bigger your angle, the bigger your radius. If you graph it with different intervals, what is that going to change about the spiral? This is not going to trace over itself. So what would the difference be between 0 and 2 pi? And then if you graph it 0 to 4 pi? About James? So this has to do with like your theta min and your theta max. So we've said before that basically if we go higher than 2 pi, a lot of times it traces over itself. But this won't trace over itself. Since we're drawing a spiral, what will happen?
Make a spiral that actually goes bigger.
Yeah, you're going to see more revolutions of the spiral. Okay. So let's start with zoom 6. Okay. Zoom 6 does 0 to 2 pi. Okay. Then set it 0 to 4 pi. Okay. Well, what's going to happen here is your radius now can hit a maximum of 12.56. Our window is no longer sufficient for that. So let's make it negative 15 to 15. Or you could just do zoom out. Okay. Also keep in mind this isn't going to look proportional. This spiral should look somewhat circular, okay, but this is going to look longer than it is wide. I'm sorry, longer than it is tall. Okay, that's because of my window. And then if I go 0 to 8 pi, we'll get a little bit more of the spiral. And let's zoom out as soon as it draws it. So we should be getting 0 to 8 pi. That's 4 revolutions of the spiral. Now you could try to figure out different things to do with the spiral. Maybe you could figure out how to make it spiral the other way. You could try things like maybe putting a negative in front of theta. Well, it's still spiraling the same way. Didn't spiral in a different direction. But you could also try messing around with theta min and theta max. Okay, maybe, I don't know, try different things and see what happens. Okay, any questions on drawing that spiral? I think I have one more thing we can try with the spiral. Let's try setting our parameter from negative 4 pi to 0. Okay, let's zoom back in. Okay, don't go all the way to 8 pi. Just go to 4 pi so you can see it bigger. Right, so there's our old spiral. And we're going to go negative 4 pi to 0. So instead of spiraling from the center out, this one's spiraling in towards the center. Okay, and I can get rid of negative theta if that's confusing people. There's your graph, spiraling in towards the center. So again, that's called the spiral of Archimedes. Okay, any questions on that? Anybody have any general questions on the calculator? Just how you graph something, parametric, polar, or function? Okay. All right, so the homework, it's on 493. Okay, there is a decent amount of sketching to do, so if you have a calculator handy, you probably need that for the homework. But I'd like you to try 19 to 22, 24, 25, 30, and 31. And then 33, 37 to 41, just odd. And 43 to 49, just the odds. Okay, so we'll take a look at that tomorrow. And that finishes up everything that we're going to do with parametric and polar.